So, man, it's going. Had to get some lab stuff ran this morning at the VA. Yeah. It was actually really quick. I was surprised. I was in and out almost as quick as boot camp. Yeah. I didn't even feel the lady prick me this morning. I was like, "You took blood?" Yeah, and I gave what do you call it? An additional vial for they're doing like 1 million veteran study, and what they're doing is they're studying cancer, like indicators for cancer in your blood. Yep. So they'll probably call me soon. You're going to have cancer very soon. That's not cool. Wow. Like that a biatch. Awesome. God damn it.
I think we're just
This is obnoxious. Das ist 3, 22.
all right. Any questions before we get started here? So today we are going to do a modal impact test, and just want to go over some of the components that we're going to use. This shows an image and some of the main points of the modal impact test that we're going to do. The first thing I want to draw your attention to is this part right here. This is the impact hammer. I think you got a picture of something like that in your notes. It's a little small. Zoom in on it right here. I'm pretty sure it's the same one I've got with me. I'll show you the parts then. But there's a cable coming off of that. This, you see this yellow or orange piece of foam. Underneath that is the dynamic signal analyzer that I use. It's designed to interface with a laptop. And so this particular one is the same one I've got with me here. It's got 2 input channels, channel 1, input channel 2. It's also got an output channel, which I guess is tough to see, but in any event, we're not really using the output channel. But if we were going to drive a shaker, or if we were doing like controls demo, we wanted to drive an input, full course side beach, like you would bring a small servo system, and I use that output to drive the system with step input or swipe sign input, or whatever you use, random input you want. But it's capable of any output. We're not going to use any outputs today. We're just going to use the 2 inputs. There's also an accelerometer. This is a real small one that I have here. This is a turbine blade. We're not going to do anything that complicated because the geometry is pretty involved, and I want you to be able to generate your own geometry in SolidWorks. But this is just a picture I took in the lab for some demos, different parts. And so what we're going to do today is we'll show you the 2 components, sensors that we're going to use. We're going to show you the analyzer. I'm not sure I'm going to be able to get much of a better image than what you have right here of the analyzer. I'll send you the camera. And then we're going to actually demo things. But before I actually do the test, I have to talk about the setup. So the setup is a very important part of any test. And one of the things that you'll see, I will actually specify the sensitivity of the hammer and the accelerometer. Let me ask you a question. The sensitivity for a dynamic sensor like a piezoelectric load cell, piezoelectric accelerometer, is sensitivity for a single frequency?
No.
Or is it for a range of frequencies? Range, why? Why would we want to know sensitivity over range of frequencies? Because we're going to be measuring over there. We don't know what the frequencies are. We don't know what frequencies, but we're going to be measuring over a range of frequencies. Right? So that was the whole point of talking about frequency response today. And of course, that's the important point. It's flat. We're interested in using these sensors over a frequency range. So the hammer and the accelerometer that we use are going to have the same sensitivity over the frequency range. All right, which is well over 2,000 hertz and down to 10 hertz. Because it's a hammer, it's a transient event, meaning we strike a structure. I brought a couple lightweight structures with me here. If we strike a structure, the force that we're applying is going to occur in just a fraction of a second. All right, and the response isn't going to last much longer. So if we're just looking at a scope or an analyzer output, we're not going to see much. It's gone before we even really see it. So we have to trigger it. It's called trigger. So you can trigger off something. What do you think is a good signal to trigger off? Do you have any idea what triggers? Are you like a little bit more? Yeah. All right. So any analyzer, I think you use scope. Yeah, you should use scope, of course. You guys use scope. Right. I have one. You had to trigger. You did that. You had to use the trigger feature if you actually captured the transient measurement. Right? So measurement. What do you think trigger means? Yeah, basically something that says, hey, that signal, start collecting. All right, that's what a trigger is. So in this case, there's lots of things you can trigger off. What you can trigger off the hammer input, you can trigger off response input. Those are the only two inputs that we've got. Which you think would be the better one to trigger off? Anyway, why? Nice clean change in voltage. All right, so that's what it is. We'll look for a change in voltage. Susan sees that on channel 1, right set it up, it's going to start grabbing data. In fact, I tell it, hey, not only grab that data, grab some data before that. It's called pre-trigger. All right. The other thing is important, we have to set up the input settings. And I'll talk about what we did, but there's a bunch of different settings that we have to set up. Averaging, how many averages we take. In fact, that's because of the fact that my arm's not kind of well calibrated. I like to take averages. Yeah, average out any noise that occurs. So we're looking at the best data. Now, also have to set what's called the bandwidth of the test. We used that word the other day when we were talking about bandwidth. Estimates for determining bandwidth from previous response measurements. Well, bandwidth can have different meanings. Of course, we're talking about zeta measurements, damping ratio measurements. It's the power points define the bandwidth. You guys remember what I'm talking about? All right. For peaks around resonance. For measurement, a bandwidth is the range that you're looking at. Right? The frequency range that you're looking at. Record length is the amount of time that you're looking at. All right. And also, I'm going to show you some different traces. There's some different data. We'll look at the time domain data. We call that time traces or time records. We'll look at the auto spectra. We talked about them just briefly. I told you not to worry too much about that page, but we'll talk about the auto spectra and power spectra. Those two quantities are used to calculate the frequency response. I like to look at those and make sure, and I'll show you some of the issues that run into that. I like to look at those to make sure that the data doesn't have any problems. And one of the problems that can occur, I brought fairly bigger structures today, but I have used really small ones in the past. And one of the problems with really small structures is it's hard to hit them easily without a bounce. Bounce is you have problems with your data. You can see it pretty clearly in this vector. Anyway, so I like to look at those. What do you think the force vector will tell us of the hammerhead? What's the time trace of the hammerhead going to look like? It's going to be a pulse, right? And what do you think the spectra is going to tell us? Spectra tells us the frequency content, right? And so it's like a Fourier transform. It's another step beyond that, but it gives us the same information. Frequency content. For a hammerhead, what's that going to look like? What should it look like? It should be pretty flat, right? It should be pretty flat, meaning we're exciting a range of frequencies about the same level. It is what you want to do in a test. You want to excite a range of frequencies at the same level. If I'm exciting certain frequencies at a higher level and other frequencies at a lower level, then I can't really look at least the magnitude of my response with any field. We can't extract mode shapes. I can't really look at it can't really depend on the magnitudes very well. I'm not exciting the frequencies very well. All right, so we're going to look at that data on the thing, on the laptop that I have with me here. And then also, the analyzer that I have is called SigLab, and it was designed to interface with MATLAB. So the software, the hardware interfaces with MATLAB. And so as far as post-analysis of any data, or reviewing the data generally will use MATLAB. So I've written an M file. You don't have to write it, but you have to use it. So the data that we collect will be have a name, file name, .dna. DNA stands for virtual network analyzer, and that's the analyzer we're using. But in any event, we're going to have a couple of files from each test, and all you have to do is go into this M file, called data plot.m, and just change the file that you wrote. The only thing that you have to change. All right? I wanted to show you that. So this file is a couple of slides long, 2-3 slides long. I just want to show it to you. Most of it's just pulling in the data from the format that it's saved on SigLab, and then loads in the data, and then pulls the data out of the file, and then plots it. That's all it does. It's a little long, but it's, and I just uploaded it Tuesday to Kansas City. Have it. There you have it. So I don't know if you guys have written an M file before. All right. Why would you use comments on an M file?
Make it easier.
You know what's going on. So comments are what's in green. First character is the percent sign. What's the other reason you want to use comments? One of the things. So this is called data files or dataplots.m. If MATLAB knows where to find this M file, which if I'm going to use it has to know. You guys know how to set a path, right? How many know how to set a path? How many don't know how to set a path? All right, so let me explain what I'm saying. So this file, dataplots.m, is now on Canvas. I'm going to expect you to download it onto whatever computer you're using that has MATLAB or access to MATLAB. You pull up MATLAB and you type data plots, is data plots going to come up? Or is it going to say, we don't know what you're talking about, or whatever error it gives you when it doesn't know? I'll recognize the file. It's probably going to say we don't recognize it unless you set the path, unless you tell MATLAB, hey, check this folder here for stuff like M files that I'm going to use. You should set the path. I'll show you how to set the path. Should have done it. I don't know what you're doing in the 2 courses that we teach. You don't know how to set a path, but I'll show you. All right. The other thing that's useful is once it recognizes type data plots, it's going to basically spit out a bunch of figures that does with the file that's being loaded. As long as you also have the file that's being loaded in the same directory or same file folder. So you want to take your dataplots.m file and your data files, put them in a folder. Make sure MATLAB knows to look in that folder called settings path, and then run it. Now, when you go into MATLAB, one of the ways to check to make sure it's there without just typing data plots is type help space data plots. What do you think is going to come up on your screen? MATLAB. All your comments. All your comments. Oftentimes, I don't even bother opening a file, just type help space and that file name. It'll tell me what I'm dealing with or what I'm supposed to do. I don't remember the computer. All right, so this amount of information that I need is here. Retrieve the plots impact test data from SigLab.dna files, channel 1, making sure I set those particulars files properly. Channel 1 is my impact hammer. I give model, serial number, tip that I use, and the sensitivity. So many millivolts per sheet, or so many newtons per volt. You can, of course, split that in volts per newton, which is probably the way the manufacturers do it. Channel 2 is accelerometer. This is the accelerometer that we're using, serial number and sensitivity. All right. So what this does is it plots time traces for the hammer hit and the accelerometer. It plots their spectra, their auto spectra, which gives you the frequency content of both of those. It plots the frequency response magnitude and phase, and it plots the coherence. All right. The coherence is very important because if it's not close to 1, coherence is not close to 1 in the area near the frequencies where we're extracting data, then we can't really trust the frequency response. All right, so this is the only line that you have to mess with right here. This says impact test 2. You're going to change the word impact test 2 to structure. Structure H and structure F. All right, so you're going to have, I've already uploaded it because I just ran a dry run the other day. My office material equipment is still good. Structure H.DNA and structure F.DNA. Those are already uploaded. You're just going to go and change that. And what happens if you remove that dash map? That dash, how many people if you remove that? It's going to create a problem for you. And every semester somebody sends me an email, a long email about how they spent hours and days trying to figure this out, and they can't get it to work, and they send me a snapshot of the update. I showed it to me, that is gone. All right? So don't remove it. Don't go changing it. The only thing you have to do is change the word impact test to structure H or structure F. All right? H. All right, so the rest of this, just if you really were interested, you can look at it. If you're not, which you're most likely not, don't bother. This section here is the time traces. I define my time vector as time, my force vector is force, my acceleration vector is acceleration for itself. All right, this is the format that I have to extract this stuff from what's been done. All right, and the only reason I know that is because I've looked at the SIGLab manuals and I've used 20 years. All right, so I know the format. Then we start on something that you should be familiar with, right? You want to like plot a figure, open a figure window, you define figure, its axes, and so forth. Here we're just plotting force versus time, acceleration versus time. Here we're actually plotting the auto spectra, the information given in the data file. I just need to pull it out. I use ASP to denote auto spectra for both of the quantities. And then I introduce these, just give it in terms of volts. So I have to multiply by my sensitivity to get the proper units. That's why we have sensitivity defined. So those are plotted versus frequency, and then frequency response and coherence stuff is plotted. There's 3 plots here. One is the coherence. I always like to look at that first. Then I plot the magnitude. In MATLAB, I use the absolute function. It gives me the absolute value of the same thing as magnitude for my purposes. And then with respect to phase, there's 2 forms of the frequency response phase that we can look at. One's called wrapped and one's called unwrapped with a W. And what the wrapped is it keeps all of my phase information between plus or minus 180 degrees. All right, plus or minus 180 degrees. And, or if you use a radians, plus or minus pi, which I'm not using. I converted it into degrees. So when I showed you the data the other day, data that's like in the book, that phase was wrapped. Remember, all the phases between plus or minus 180 degrees. And the reason why that's preferred for testing, because then when you look near resonances, your phase is either going to be at a resonance, either plus or minus 90 degrees. right? If you got normal modes, it's going to be close. It's going to be there. You've got almost normal modes, you're close to normal modes, close to plus or minus 90 degrees. If you don't wrap it, then it's just going to basically vary between 0 and some very large negative number, and then you have to keep track how or even changes 100 degrees. You don't have to worry about that. You always wrap it. I always wrap it. But I did include, I commented it out, but I did include an unwrapped version of it. You actually have to specify it like that for at least the range of plus or minus 50. That's it. All right, this is just an example of that data that I had loaded a long time ago, and over a range of 0.5 of a second, you can see that hammer pulse is quite narrow. You'd have to zoom in on it to actually see it, right? But I can clearly see I don't have a double hit, so I trust that data. That's the time trace for my hammer hit. It's about 90 newtons, so it's not a lot. I'm just tapping it enough not to overload anything. And then this is my response, my acceleration response. This is nice because it decays within the 0.4 seconds, right? So as far as really needing a window here, I don't need it. And I think I use a window by default in this thing, but even here, I don't really need much of a window. There's not much noise going on. Yes. Out of spectrum, basically you take the Fourier, it's in the notebook, it's on the slide, and I can pull it up and show it to you. We were talking about how to calculate the frequency response. All right, we started with the FFT of each of the force input and then the acceleration response. All right, and then from there we calculated the auto spectrum. And what it used, we actually use what's called cross spectrum too. But what it uses is it uses the FFTs. All right. All right, so here's the auto spectra, and just as we expected for a hammer hit, it should be pretty flat. And it is dropping off. If we were going to use this to extract something other than natural frequencies and damping ratio, we're going to use it to extract mode shapes. I'd probably put a steel tip on it. What would a steel tip do compared to a plastic tip? The auto spectra. Would it fall off quicker, or would it be flatter and fall off a higher frequency? It would be flatter. Yeah. So a steel tip would make it real flat over the 0 to 1,000 hertz range, which, if I was going to extract, if these peaks were important, the actual value of these peaks is important, which they are for the purposes of mode shape extraction, then I'd want it to be a little flatter. For our purposes, it's fine. All right, there's the auto spectra. Certainly we see the peaks. And then the frequency response magnitude and phase and coherence are given here. And you can see these look almost identical as far as shape, auto spectrum of the acceleration, and the magnitude of the frequency response. And to some extent they should. It's more than just a ratio of this to this, but it's close to that. So if this is flat, your acceleration, your magnitude of your frequency response, which has units, output units divided by input units, acceleration divided by force, should look like your auto spectrum. All right, so this is what we're going to use. This is the plot that you're going to use for your project right here. All right, so even though all these windows are going to pop open, you don't need them all. This is really the one you're going to focus on. Now you do want to look at your coherence, and you can see near these peaks, the coherence is pretty close to 1, so we're good. All right. Here's the wrapped phase and the unwrapped phase. Exactly what I said. Every time you go through a resonance, there's a change in phase of 180 degrees. When you wrap it, it's either plus 90 degrees or minus 96. Plus 90, minus 90, plus 90. What do you think this business is down here? Going from 0 to minus 180, what's that? I've got my structure sitting on fancy suspension. It's a low frequency oscillation of the low natural frequency of whatever the structure is sitting on. This elastic foam. There's a lot of damping, but I mean, it's not, you know, if it moves around or bounces around and stuff a little bit, then it's not going to be a real clean. That's why the coherence is bad too. But that's all that is. We ignore it. You can see there might be a little bit of something down here. It might show up even more with stuff we do today because the one piece is a little heavy. But these three here are real clean. Plus 90, minus 90. All right. Any questions on this one? So what you're going to do, we're going to do two structures. You've got the drawings for the structures. I didn't give you the drawing files, but I gave you the drawings to show dimensions and material. I already uploaded those to Canvas on Thursday. I uploaded the data files. One's called structure F.VNA, one's called structure H.VNA, and then the drawings, I think they're called structure F and structure H.PDF. They're just the PDF of the drawing, SolidWorks drawing information for each dimensions of material. What you're going to do for both of these, I don't remember how many natural frequencies we're going to follow up, but if this is, for example, your frequency response, what you're going to do, if this was one of the frequency responses for one of these, you're going to have, in this case, 3 natural frequencies. So you would basically save this figure. I'll show you how to do that. Save this figure, and then you're going to zoom in. Have you guys ever used the zoom in feature on MATLAB figures? All right, I'll show you how to do that. Right, so you're going to zoom in on each one of these. Why do you think you want to zoom in on these? You got to extract the damping information. Right? So to do that, you can't really, I mean, I can't see the frequencies here. So neither can you. So you have to zoom in on these, get your bandwidth for each one of these peaks, get your natural frequency, get your bandwidth, and estimate natural frequency of the animation. So it's pretty simple. That's why I said it's more like a homework problem. It's not really a project. It's easier than homework. So in this case, you have 3 natural frequencies and 3 damping ratios. Make one, or if we're using Hertz, F1, F2, F3, zeta 1, zeta 2, zeta 3. All right? Any questions? Before I go over to this other thing, let me. Projects, here we go. So here is a description of the projects. And like I told you, there's not much to them. I hesitate to call them projects, but I didn't want to call them homeworks. You already have homework. Project 1, you're going to extract natural frequencies and damping ratios from frequency response measurements. We're going to use the magnitude plot. That's the one that I just pointed to. That's the one that you can use. 2 different components from the classroom mobile testing that we're doing today. We're going to summarize the results in a table for each component. I don't remember the number of modes for each one, but it's like at least 2 or 3, something like that. We'll look at that in a minute. So, you know, it's something you can easily do in a couple of pages. I'll be very specific once we pull them up as to what I want you to do. But that, I mean, that's it. As far as how many natural frequencies and damping ratios you have to extract, how many plots the figures you have, I'll give you that. Project 2 is to do an FEA analysis, and I always state to use SolidWorks because I know that that's, you know, let's use that. We'll go over FEA in the coming weeks, a couple of weeks. And for this, you're going to show your FEA work, which includes meshed images of your components, and then a table of your computed, FEA computed natural frequencies compared to your measure. So what we're doing in project 1 is measurements. What you're doing in project 2 is computing and comparing, right? Any questions on that? All right. So, so you can can see MATLAB in the background there. I'm going to open up the one. Holding structure first. All right, so this particular test, you know, you could say there's two real dominant. So this is already showing the magnitude of the frequency response and what it's showing. And I'll go through, review the test, and show you all the other plots as well. But in this case, there's two dominant peaks. There's one around 1400 hertz and another one just above. Right? But I'd like you to also look at this one close to 200. I mean, I guess you could try to do something with those, but honestly, I'd ignore those. So look at this one that's about 250 here and here. So this first structure F, you have 3 modes. All right. So let's just talk about the setup. So, like I said, you can see MATLAB in the background. Once I pull up SIGLab's virtual analyzer, it pulls up this output window, which shows my data, and then it also pulls up this setup window. In the setup window, you have 4 quadrants. The top left quadrant is my channel setup. And you can see right here it displays channel 2, but I have the option, of course, to pick channel 1 and channel 2. The number below the channel number is a voltage level. And what do you think that is? No. So one of the things that you always have to set up, you've done this on this oscilloscope in lab 1. The TA did this when you did the balancing demo in the lab. Yeah, you have to set the input range. You have to set the input range. What if you don't set the input range? What are the 2 possible bad things that could happen? It's nothing to do with calibration. So let's say we're trying to measure a 10 volt signal and our input range is set plus or minus 5 volts. What's going to happen? There's a word that we use.
Quantitation.
Yes.
Quantitation.
Really? So, okay. Nobody's ever done anything with audio in here either. Right? What do you do with audio?
Well, you got to filter it.
So you're trying to take a 10 volt signal and put it into something that's set up for a 5 volt range.
I forget the word.
Overload?
It cuts off the top of the clipping.
Red light flash? Any of these things probably would work. Okay. Overload? Does that make sense to you? That might be a word that you use. Overload? No?
Clipping. But we don't.
All right. All right. You try to measure, so you have to set up your input range. You're right out of the line. All right. You have to set up your input range. So if you look at the possible input range, right here for channel 2, the possible range is I could set it to auto, which is the thing I never like to do that. People do that. 20 millivolts, 39 millivolts, 78 millivolts, all the way up to 10 volts. That's plus or minus. All right. I had this test set to 5 volts plus or minus 5 volts. That's my acceleration. Accelerometer. The accelerometer must be pretty sensitive. I'm not hitting these things very hard, and I could get a bigger signal with that range. So if I tried to set it lower, if I set that down to plus or minus 2.5 volts, what do you think would happen? Same question. Same question. Overload. Overload. If I range overload. I'm trying to put a signal that fits nicely in the plus or minus 5 volts. I'm trying to put it into a range of plus or minus 2. So what do you think an overloaded signal looks like? Give me a nice, beautiful sine wave like this, but it's big, and you're trying to measure it here. So what happens? Flat, it clips. So you're right on. So those are the words I was looking for. Clipping, overload, even our red indicator light. We don't have, we have virtual old LED here. I don't really space. That's it for overload. We want these lights to be green. They're virtual lights, but a real analyzer, the one that you use for, an analyzer that has real LEDs on virtual LEDs, like the one you use for balancing. Remember when she was doing the test? There, we're all there, right? Your indicator lights near the channels. Remember, they were yellow, they were green, yellow, and then red. Remember any of that? I probably didn't talk about it. Maybe I didn't talk about it. Normally, when you run that test, you actually start taking data. When it's going through the range of speeds, it doesn't matter. Once you start taking data, you want the 3 green lights on each channel. What that indicates is you're using whatever range you set. You can tolerate a little bit of yellow, but you don't want any red. It's red. You've got a red indicator light on its own. All right? In the audio world, with mixers or any sort of preamp, you usually have some sort of an indicator light that's overloading. You tolerate a little bit of measurement. Same thing. Usually you have it. All right, so if you don't pay attention to that, if you overload or if you try to put too much signal into an input range that an analyzer, it will clip / overload those means the same. All right? And then are you really measuring what you think you're measuring? No. You're measuring clip signals. All right? All right. So the other extreme, you're not. So what happens if your signal is like a millivolt, or let's say a tenth of a millivolt, and I set my input range to plus or minus 10 volts?
You don't see anything.
What happens?
Nothing to see. It's flat.
So that's fair. You don't see anything. You'll see something, but is this digital? Yeah, all analyzers are digital. Unless you've got really old vintage stuff, right? You know, I do, but it's digital. Do the vintage stuff. All right. So what do you know about anything digital?
Screen.
There is going to be some resolution. Okay, terms, right? In other words, if I give you an 8-bit A to D converter, it's an analog to digital signal. There's 256 possible values. So if I set my input range to plus or minus 10 volts, I got 256 possible values. With by 20 by 256, what do you get? Something bigger than a millivolt, right? Or something millivolt. So you're going to be way down in the digital noise range. Your resolution is bigger than the signal that we're trying to measure. All right? So you're down in the noise. So what we say, I always just say you're down in the noise. Electrical noise, certainly down there. Digital noise, you're down there. So you're going to have a lot of noise. And what we say when we're taking measurements is that you're going to have poor signal to noise. Poor signal to noise. All right, so that's why on a Honosuke analyzer that you use for lab balancing purposes, 3 green indicator lights, those should be on. No red lights. These green lights should be on. No red lights. See red lights, then I should need that. They're about setting my input range. All right. Also, if I'm taking measurements and everything looks really noisy, I may just have way too big of a range set for the amount of signal. All right, so this isn't something that you're going to necessarily, we're responsible for doing tests. This isn't something that you wouldn't necessarily remember, but from just a quick lecture like this, if you're doing this for a living, it's something that you need to be very aware of.
All right. So that's the input range. And like I said, channel 1 is set to 5 volts. Channel 1 is set to 78 millivolts plus or minus. Well, look, next to that, we have something called bias. Bias is something that we use in engineering to define just a low level voltage, DC voltage. And that is one of the input settings, a special input setting that allows piezoelectric sensors like the accelerometer camera that we're using to be directly connected to one cable. So we basically go straight from these sensors, hammer sensor and accelerometer straight into the analyzer. The analyzer, so that fits bias on my input setting, input channels, is providing a low-level voltage that's powering the built-in electronics in both of those. Why do we built-in electronics in this sensor? Yeah. What? Yeah, so what would the signal be without the built-in electronics? Remember we're talking about piezoelectric stack? Picovolts. Picovolts. So the built-in electronics are changing it from a charge. Remember pico? How big is pico?
10 to the negative 12.
Small. 1,000 times smaller than now. So pico is very, 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 very small. So picocoulomb level signal is what we're getting. All right. So internal electronics convert that to a millimeter level signal. It's very important to be able to do that. So the bias input settings provide the power to do that. The other two input option settings are AC and DC. So the AC setting, what that means is that we are actually setting AC settings filter out any DC offset. All right. So if you're measuring something that you know has no DC component, or it does have a DC component, but you're interested in the fluctuations, the AC, how to say it, the part that varies, which you call an AC part, then you use an AC setting. What that does is it filters out the DC. Let me give you an example. Let's say I have a voltage joint, and I'm measuring the force in that voltage joint, but I'm not really interested in 1,000 pounds of preload. I'm interested in the fluctuation about 1,000 pounds. Would I use DC setting input? Would I set my input channel DC or AC?
AC.
AC. So there's reasons because I'm interested in AC. But the other thing is that 1,000 pounds, that huge DC would take up most of my input range, and the fluctuations would get lost in the noise. You know what I'm saying? That's why we have that option. That's AC/DC setting on the input of any dynamic analyzer exists. Bias is something special that we have in vibration. All right, so that's it for our input channel. Down here, you can also set your labels. So I put a hammer force label, my sensitivity. I put that stuff on there for both channels. I define those hammer, accelerometer, the appropriate sensitivity. Here we set our bandwidth, which is basically our frequency range. You can see in the data, it's going from 0 to 2,000. And so that's the bandwidth for the measurement. AA filters on by default. What do you think that is? Yeah, my anti-aliasing low-pass filter. AA filters are on by default. My record length, that's how many data points we're collecting. It's always a power of 2. Why? Why is it always a power of 2? What?
Number of bits.
So I mentioned it, but you may not remember it. But it's a power of 2 because the algorithm that's used to calculate the Fourier transform is based on what's called the fast Fourier transform algorithm. And it requires that your data be collected in numbers that are powers of 2. So you see the lowest level is 64, the next level is 128, so forth, all the way up to 8,192. I always just use the maximum amount of data because it gives me a little bit of better resolution. All right, this also has a zoom feature. What you'll notice when you start trying to extract damping ratios is that you're going to see that when you start looking point to point, that the resolution in the frequency range is not as fine as you'd like. And so we could use a zoom in feature. So you could have hundreds of data points around each peak instead of just maybe a few. All right, we're not going to use that for our purposes today. But if you were to do research or work at wherever you're employed as an engineer or your own business or whatever, if you're going to try to publish this or use it with product specifications, you can usually get more data by just using this. All right, down here we have processing features. Here we're basically going to do an average of 4. There's an overload and double hit. That's what these abbreviation stands for. It's going to reject any overloads and double hits. It doesn't always work, so I always do try to keep an eye on the color of these two virtual indicator lights, overload lights. As long as they're green, we're good. And then it uses an F20 exponential 0.1 for my windows. So those, remember we talked about transient windows for transient effects. The F20 means 20% of my time record is going to get multiplied. First 20% is going to get multiplied by 1. The remaining 80% of my force input is going to get multiplied by 0. You guys remember that for your force input? The acceleration response is going to get multiplied by an exponential with a decay rate of 0.1. That's what the F20 exponential 0.1. This last corner here is my trigger. It's going to basically trigger on channel 1, which is where my hammer is, and it's going to trigger whenever it sees a voltage that is at least 18% of my input range for channel 1. So this can be a little tricky to set up if you ever try to set it up. And you'll see, I don't think I'll struggle too much with these tests because these parts are a little bit bigger than some of the ones I usually bring. But I have to basically strike these things and generate a force and therefore voltage that is at least 18% of 78 millivolts. All right? If I create a voltage that's bigger than 78 volts, what happens? Overload. See a little red light flash. If it's less than 18% of 78 millivolts, what's going to happen? Nothing. It's not going to collect any data. So I do have to be careful. You'll see I'll try to strike it a little harder, a little softer. And every time I strike it, I might not collect data because those are the things that need to be met. All right, and this delay of 10%, that's just how much data before the trigger is collected before the trigger, so 10% is collected. So I want to just go through and show you a couple things here. This is showing the magnitude of the frequency response and coherence, but we can of course look at time data. Here's both the green curve there is the green curve that you see is the hammer hit. And what this shows is that we're looking at about 1.5 seconds of data. All right. If I click on that, it's going to bring up that white curve that you see in the background. It's not as small. I could just look at that channel by itself. Looking at both channels at the same time. So if we just look at channel 2, I'll have better control over it. That's my acceleration response. So that's decaying out. I don't really need any window on that thing other than if it's always putting the hammer down. So that's the actual acceleration response. I don't remember what this was, but it decays pretty quick. Not a whole lot of it. We can also look at the spectra. So I'm going to go back to channel 1. There's my impulse. And now what I want to do is I want to look at the spectra, the magnitude of spectra. What I see there, it's pretty flat out to like 800 almost 1,000 bricks. Yeah. If I put a steel tip on instead of a plastic tip on, yeah, it would expand that out. And I might do that. Yeah. Plastic. Similarly, look at the out of spectrum of the second channel as well. And you see here, we can look at the transfer function and the coherence. To do that, we need to actually have both channels. All right, so what I'm going to do is I'm going to look at the transfer function, and we will, one other thing I want to point out. So that scale is on the dB scale of the vertical axis, which is, essentially just the log scale. That's what this right here indicates, decibel level scale. If I just look at log, it's going to give us something that looks pretty similar. That looks quite a bit different than the linear scale, right? A log scale tends to do what?
Linearize.
Well, the log of 1,000 is what? Based on what? 3. The log of 1 is what? 0. The log of 0.1 is what? What? Yeah. So what tends to happen is it brings this huge range in a linear scale. It brings it and compresses it together. So the real small stuff on the log scale gets brought up, so you can see it, and the real big stuff gets pushed down. It compresses it down. Use it in acoustics all the time. Use it in controls all the time. And we use it sometimes in vibrations. But if we just go to a standard magnitude plot, then we see this is what we got. In this case, on a regular linear scale, the big stuff dominates and the small stuff you can't really see what's going on. You don't really see anything. For our purposes, we'll just use the linear scale. All right, so the first structure, I'll try to put this over on here so you can see it. So I have a lot of parts made out of steel and aluminum, but I also had a student a few years ago making these parts that were made out of PVC acrylic. So this is an acrylic part. This is structure F, and you have a drawing on canvas for that. Gives you the material, which is one of the selections in SolidWorks. So you can pull that up if you do the FDA, which we haven't talked about yet, but it's in there. Acrylic, and the dimensions are given. This is the hammer. I don't know how well you can see that, but there is the plastic tip. It's a hard plastic tip, the load cell, and then the rest of this really is just has some built-in electronics, and then coming out with the DNC cable for the MRs. The accelerometer that I'm using has a coaxial micro diode 1032 cable on the end of it, and I use beeswax to connect this to the structure. So I've already got some beeswax on there from the other day, and so I'm just going to mount the accelerometer there, and then I put a little X there to indicate where I want it to hit the thing. And so the test is basically going to be that. All right, there's not much to it, but you can see it wouldn't take much to overload that. It's not a carpenter's hammer, which is easier, I think, a little more work, but it also helps you guys stay in. But in any event, that's it. You notice when I hit, I tend to pull back because I'm trying to avoid double. Sometimes little structures come back. All right, so that's all I'm going to try to do is do 4 clean hits like that. And we'll look at the data as it's collected. Once we get 4 clean hits, we'll take that data and it's going to look exactly like the data I uploaded. So I'm getting it in the same spot. Now, when you do your FEA analysis, one of the problems is going to be that you're going to actually compute more natural frequencies than what we measure. Why might that be? One, that's the one good answer. Any others? What? Yeah, go ahead.
You're hitting it in one
Yeah,
spot.
I'm hitting it in one direction. I'm measuring it in one direction. So, you know, it's possible that there's a mode that it's around over here is not going to pick up, or me hitting it there is not going to pick up. So when you calculate, you're going to have all kinds of frequencies. What you measure here today, what we measure today is only going to be a limited set of that. All right? Now we can move it around and put more accelerometers on it and get a bunch of different places for data. But the purpose of this is not to do an exhaustive test. The purpose of it is to do a test, to show it to you, and then give you some data to help validate your FEA analysis. All right, so I'm going to go back to this. You can see, obviously, it was a pretty sloppy hit. But I'm going to basically average. It's going to start my average test. And you can see up here it says average 0. Once we get to 4, we should be good to go. All right, it's not too bad. One of the reasons we're getting a little bit of noise up here is that my hammer is falling off. My hammer is falling off. If we go back and look at that, I can put a steel tip on it, try to clean that up a little bit, maybe I will do that. So, yeah, I'm running out of time. So if we put a steel tip on it, the noisiness on this high peak would go away. All right, if you clean it up a little bit, maybe I'll still do that. But in any event, for your project, I want you to extract this one around 250, one around 1400, and around 1850. All right. The other test that I'm going to do is that structure. F. This is structure H. Let's see as much of the story what this one looks like, but it's PVC. So there's a drawing with the dimensions and the material, and it's a little heavier, so the test is easier to perform. But I'll just use the same setting here. Oops. So I have to stop that. All right, so anybody see the problem? And we'll have to give a little later. All right, still overloading. So what I'm going to do, what should I do? You tell me. Increase the range in channel 1. So it's at 0.78. I'm going to bump it up a little bit, start that test over. All right, then we'll run into the same problem up here. I'll try to rerun it with a stiffer tip so that it's exciting a broader range of letters. So it's getting some noise in the fire. For this structure, I want you to just extract the two. Between actual frequencies, 2 damping ratios. I do have 5 minutes, and instead of putting a steel tip on here right now, what I want to do is I want to go into MATLAB and pull this up. So I'm going to go in and open data plots. All right. And all I need to change is this right here. Instead of structure 20, let's do the first one, structure F. Now I'll come back down here, write data plots. All right. This is the magnitude. This is the one that I want right here. Doesn't look like the right data, does it? Let me try to structure each. Maybe it didn't save. Maybe I have to save it. All right, that's the right one. That's the right one. So I think you have to save it. Older version. All right. So for this structure H, how many plots are you going to need? 3. This one and 2 more. So you're going to want the magnitude of the frequency response, and then you're going to need to zoom in on these 2. Let's take a look here. How do you zoom in? Magnifying glass. All right? Grab that magnifying glass and draw a window like that. All right? Now you can grab this peak here. This is another way you can pull this data right here, this line with a plus on it. You can pull data points. So we see that our frequency is 1751. Our magnitude is 18.98. So we take that 18.98 multiplied by 0.707. That gives us our bandwidth. All right. We hit the negative sign. It pulls us back. So that's a plot that we can want to save right there. Here we go. Okay. We can do the same thing here. Zoom in on this one. Even do a little bit better than that. Again, take the peak value here. That's going to define our frequency. Multiply that 7.98 by 707 that would define our bandwidth. Let me just go ahead and make sure I've got the right data for the other one. For you. Yeah, there it is. So in this case, how many plots are you gonna have for this? This is structure F. 4. That one here, and then you're gonna have 3 zoomed in. Zoom in on this one, zoom in on this one, zoom in on this one. Can I see that one smaller there? So your project 1 is gonna have a total of how many figures? How do you get these figures, by the way? You go up to edit, copy figure, just paste it right in the Word. So project 1 is going to have 7 figures, 2 tables, right? And you're going to show your work for extracting natural frequency and calculating damping ratio, right? Show your work for that. Don't just show the numbers. Say, oh, I did it in a spreadsheet. Do a spreadsheet, it's fine, but show your work. It's not that many. All right? You should be able to do that in a couple pages, right? I mean, I'm not going to force you to 2 pages. 2 pages. We'll make it due a week from today. All right? Our paid class, yeah, our copy class, we'll just collect it in class. Yes. Just put your name on the top, yeah, nice big letter. All right? All right, thanks. If I can get you to hit the lights on the way out right now, that'd be great.
He wants natural frequencies, damping ratios. That's it. Huh? Oh, and the bandwidth. What?
You got it listed. Like, it's pretty.
Okay.
I mean, I'm above everybody. Set up with now.